In the middle of the night, in one of the most remote, most seismically violent stretches of land on the entire planet, the ground moved hard enough to wake people out of a sound sleep. A magnitude 5.8 earthquake struck just after midnight local time, 73 kilometers east of the city of Petropavlovsk-Kamchatsky, in Russia's far eastern Kamchatka region. And within minutes, seismologists thousands of miles away were already staring at one particular number on their screens. A number that, on its own, doesn't sound like it should matter much, but actually opens up one of the more genuinely interesting questions in earthquake science. How deep did this thing actually happen? And what does that depth tell us about what's really going on underneath one of the most dangerous fault systems on Earth? Most people, most nights, never think about what's happening dozens of kilometers beneath their feet. The ground feels solid, permanent, done with its business ages ago. But underneath a specific stretch of Russia's Far East, something enormous is still actively working itself out. A process set in motion more than a year ago, still very much unresolved, still capable of jolting people awake in the middle of the night, till generating exactly the kind of data seismologists comb through the moment it arrives, looking for one specific number that can tell them far more than the magnitude alone ever could. Here's the number causing the stir: 55 kilometers. That's how deep this earthquake occurred beneath the surface, according to initial reports. And if that number means nothing to you yet, by the end of this, it will mean quite a bit. Because in earthquake science, depth isn't just a technical footnote buried somewhere in a data table. Depth is one of the most important clues seismologists have for understanding what kind of earthquake they're actually looking at, what caused it, whether it's connected to something bigger, and critically, whether it carries any risk of triggering a tsunami. And this particular earthquake didn't happen in isolation. It happened in a region that, just over a year earlier, produced one of the most powerful earthquakes ever recorded by modern instruments, which means every new tremor here gets read not just on its own terms, but as a possible chapter in a story that's still very much unfolding. Let's set the scene properly, because context is everything here. On July 29th, 2025, just after 11 in the morning local time, a magnitude 8.8 megathrust earthquake ruptured off the eastern coast of the Kamchatka Peninsula, roughly 119 kilometers east-southeast of that same city, Petropavlovsk-Kamchatsky. To put that magnitude in perspective, it was the most powerful earthquake recorded anywhere on Earth since the catastrophic 2011 Tohoku earthquake in Japan, and it ties for sixth strongest ever measured by modern seismometers, in the same tier as the 1906 Ecuador-Colombia earthquake and the 2010 Chile earthquake. The rupture itself took roughly 3.5 minutes to fully play out, an almost unimaginable span of time for the ground to be actively breaking, as the fault slipped by as much as 30 feet along a stretch of the seafloor. That slip happened along the Kuril-Kamchatka Trench at a depth of about 35 kilometers, on the boundary where the Pacific Plate is slowly, relentlessly diving beneath the Okhotsk microplate. Because the rupture occurred at a relatively shallow depth on that subduction interface, it shoved a massive slab of ocean floor vertically upward, displacing an enormous volume of water above it. And that displacement is exactly what generates a tsunami. Waves ultimately reached run-up heights of over 33 meters in places, triggering Pacific-wide tsunami watches and warnings, forcing evacuations from Kamchatka all the way to Japan and Hawaii, and leaving the town of Severokurilsk partially submerged, with roughly 2,000 residents evacuated as the water surged in. Remarkably, despite the sheer scale of that main shock, the human toll was limited. 1 indirect death and 25 injuries, most of those also indirect, largely because the region is sparsely populated and had functioning early warning systems in place. But the ground itself didn't just shake and stop. Preliminary GPS data from Russian seismic monitoring showed the southern part of the Kamchatka Peninsula physically shifted southeastward by nearly 2 meters, comparable in scale to the crustal displacement measured after the 2011 Tohoku earthquake in Japan, one of the most closely studied megaquakes in modern history. That's not a subtle geological footnote. That's the literal ground moving permanently by more than 6 feet. And here's the detail that matters most for understanding everything that's happened since. This earthquake wasn't a single, isolated event that struck and then went quiet. It arrived at the tail end of a 10-day sequence that had already produced 50 earthquakes of magnitude 5 or larger, including a magnitude 7.44 shock on July 20th and 3 separate magnitude 6.6 quakes in the days leading up to the main event. In the immediate aftermath of the 8.8 itself, the United States Geological Survey issued an aftershock forecast that read almost like a warning label for the region's near future. A 2% chance of an additional magnitude 8 or larger aftershock within the first week. A 24% chance of another magnitude 7 or larger. a 96% chance of a magnitude 6 or larger, and better than 99% certainty of continued magnitude 5 and magnitude 4 aftershocks. In the months that followed, that forecast proved accurate. By September of 2025, a magnitude 7.8 aftershock struck the same general region at a shallow depth of roughly 10 kilometers, again briefly triggering a tsunami threat before it was lifted. Through the rest of that year and into the following spring and summer, the sequence kept producing significant earthquakes. A magnitude 6.6 and magnitude 6.0 pair striking within a minute of each other in June of 2026. A magnitude 5.8 in July, another significant cluster in early August. As of the most recent full accounting, more than 3,700 aftershocks of magnitude 4 or larger have been recorded since the original rupture. Which brings us back to this latest earthquake, the one that struck in the dead of night, 73 kilometers east of Petropavlovsk-Kamchatsky, at a depth of 55 kilometers, more than a full year after the original megathrust event. On the surface, the obvious, almost automatic assumption is that this is simply one more aftershock in an already long, well-documented sequence, the Earth continuing to settle and adjust after the largest rupture it's produced in decades. And that assumption might well be correct. Preliminary reporting from regional monitoring services has already characterized it as likely being part of that ongoing aftershock sequence. But the specific depth of this particular event is exactly the detail that makes a genuinely careful seismologist pause before simply filing it under more of the same, and understanding why requires digging into what depth actually tells you about an earthquake's origin in a subduction zone like this one. Here's the core distinction that matters, and it's one most people have never had a reason to think about. In a subduction zone, the kind of boundary where one tectonic plate is sliding or subducting beneath another, earthquakes don't all happen in the same place or for the same reason, even when they cluster in the same general region on a map. There are, broadly, two different categories of earthquake that can occur here, and they behave very differently. The first is what's called an interface earthquake, or interplate earthquake. This happens directly along the boundary where the two plates are grinding against each other, essentially the seam between them. This is exactly the kind of earthquake that produced the original 8.8 megathrust rupture, occurring at a depth of around 35 kilometers, right along that plate boundary interface. Because these earthquakes involve a large, relatively flat fault plane moving vertically, they're extremely efficient at displacing the seafloor above them, which is precisely why they're the earthquakes most capable of generating major tsunamis. The second category is fundamentally different, even though it happens in the same broad region. These are called intraslab earthquakes, or intraplate earthquakes, and they occur not along the boundary between the two plates, but within the subducting plate itself as it bends, stretches, and fractures on its way down into the mantle. Think of it like this. As the Pacific plate dives beneath the Okhotsk microplate here, it isn't sliding down smoothly and rigidly. It's bending, the way a long sheet of metal bends when you push one end of it downward while the rest resists, and that bending puts enormous internal stress on the plate itself. Stress that eventually has to release somewhere, often through fracturing, that has nothing directly to do with the plate boundary interface a few dozen kilometers above it. These intraslab earthquakes tend to occur at greater depths than interface events in the same region, and critically, because they don't involve the same kind of large-scale vertical seafloor displacement that a shallow interface rupture produces, they generally carry a much lower tsunami risk, even when they reach a significant magnitude. This is exactly why the 55-kilometer depth of this latest earthquake is worth pausing on. The original main shock ruptured at roughly 35 kilometers, consistent with a classic interface megathrust-style event along the plate boundary. A quake occurring at 55 kilometers, noticeably deeper than that interface depth, sits in exactly the range where seismologists start asking whether they're looking at a genuine aftershock along that same plate boundary, redistributing stress from the original rupture, or whether they're actually looking at a separate intraslab event, a fracture happening within the body of the subducting plate itself, likely triggered indirectly by the enormous stress changes the original megathrust rupture introduced into the surrounding crust, but mechanically a different kind of earthquake altogether. That distinction isn't just academic hair-splitting. It genuinely matters for how scientists interpret the ongoing risk in this region for a few concrete reasons. First, and most immediately practically, intraslab earthquakes, even fairly strong ones, are far less likely to generate a tsunami than a shallow interface event of the same magnitude, precisely because of that difference in how the seafloor actually moves during the rupture. That's almost certainly part of why this latest magnitude 5.8 event didn't trigger any tsunami warning at all. The depth and likely rupture mechanism simply weren't consistent with the kind of large-scale vertical seafloor displacement that produces dangerous waves. Second, and more scientifically significant, if a subduction zone's aftershock activity is genuinely migrating deeper, away from the original plate interface and into the body of the subducting slab itself, that could be a meaningful signal about how the entire region's crust is still redistributing the enormous stress the original megathrust rupture introduced more than a year after the fact. It doesn't necessarily mean anything more dangerous is coming. It simply means the process of the crust finding a new state of equilibrium after a rupture this large is genuinely still ongoing, working through different parts of the surrounding structure at different times, rather than settling neatly and predictably in the exact same spot every time. It's also worth being precise about how depth affects what people on the ground actually experience, because that connects directly to something specific reported after this latest quake. It was described as being felt strongly by many people near the epicenter, specifically because of its relatively shallow depth. That might sound like it contradicts what's just been explained. 55 kilometers is, after all, deeper than the original main shock's 35. But depth is a spectrum, not a simple binary of shallow versus deep, and 55 kilometers still falls within the range seismologists generally classify as a shallow focus earthquake, since that category typically covers anything from the surface down to about 70 kilometers. Intermediate focus earthquakes run from there down to roughly 300 kilometers, and deep focus earthquakes can occur even further down than that, in the most extreme subduction environments on the planet. So while 55 kilometers is deeper than the original interface rupture, it's still shallow enough in the broader classification scheme to transmit a meaningful jolt of shaking up to the surface with real intensity, which is exactly why people near the epicenter reported feeling it strongly, even overnight, even without the event being anywhere near the scale of the original main shock. It helps to appreciate just how historically active this exact stretch of coastline actually is, because it puts the current sequence in proper perspective. The Kuril-Kamchatka arc, the broader tectonic feature this earthquake belongs to, stretches roughly 2,100 kilometers from Hokkaido, Japan, along the Kuril Islands and up the Pacific coast of the Kamchatka Peninsula, marking the entire length where the Pacific Plate dives beneath the Okhotsk microplate. In the 114 years of seismic record-keeping since 1900, this arc has produced 133 earthquakes classified as large, magnitude 7 or greater, and 12 classified as great, meaning magnitude 8 or larger. Several of those historic ruptures have generated damaging transoceanic tsunamis, including a magnitude 8.3 event near Hokkaido in 2003 and a magnitude 8.4 earthquake near the Itorufu region in 1958. In October of 1963, a magnitude 8.5 megathrust earthquake off the island of Urup generated a significant tsunami across both the Pacific Ocean and the Sea of Okhotsk, with wave run-up heights reaching 4 to 5 meters in places. And in a genuinely remarkable historical footnote, a gap in the rupture zone between Simashir and Onakatan Islands that had remained undisturbed by a major earthquake since the year 1780 finally broke in November of 2006, with a magnitude 8.3 event, only for a second. Magnitude 8.1 earthquake to strike the exact same aftershock zone just 2 months later, in January of 2007, on what researchers believe was a genuinely different fault, making the pairing one of the largest documented earthquake doublets in modern seismic history. This entire region, in other words, doesn't experience isolated, one-off, catastrophic earthquakes. It experiences long, layered sequences of major seismic activity, sometimes stretched out over months, sometimes revisiting nearly the same patch of crust more than once within a matter of weeks. There's a broader, genuinely fascinating piece of geoscience buried underneath all of this, worth taking a moment to actually explain, because it's the framework seismologists use to make sense of exactly the kind of pattern playing out here. As a tectonic plate subducts, it traces out a curved path, descending at an angle into the mantle, and earthquakes occurring along and within that descending slab tend to cluster along a recognizable sloping band that seismologists call the Warati-Benioff zone, named after the two scientists who first identified the pattern independently in the 20th century. In the Kuril-Kamchatka region specifically, this zone extends to remarkable depths. Cross-sections of the subduction zone here reveal seismicity, tracing down as far as 650 kilometers beneath the surface in places, a reflection of just how old and how firmly established this particular subducting slab has become, having been diving beneath the Okhotsk microplate for tens of millions of years. Every earthquake occurring within that zone, from the shallowest interface ruptures near the trench itself down to the deepest intraslab fractures hundreds of kilometers below, is technically part of the same overarching subduction system. But where exactly along that curving band each individual earthquake happens tells scientists something genuinely specific about which part of that enormous, slowly grinding machine is currently under the most stress. This is also where the real-world stakes of getting that depth reading right, and fast, become obvious. Within moments of any earthquake in this region, tsunami warning centers around the Pacific, organizations like the Pacific Tsunami Warning Center in Hawaii, and Russia's own regional monitoring services have to make an extraordinarily fast, high-stakes judgment call. Does this earthquake's magnitude, depth, and location suggest a real risk of a tsunami large enough to threaten coastal communities, potentially thousands of kilometers away, or not? Depth is one of the single most important inputs into that calculation, precisely because of the interface versus intraslab distinction just described. A shallow, high-magnitude interface rupture near the trench gets treated as an immediate, serious tsunami threat, exactly as happened within minutes of the original 8.8 event in 2025. A moderate magnitude earthquake at a deeper, more ambiguous depth, more consistent with intraslab faulting, gets assessed very differently, which is exactly why this latest magnitude 5.8 event didn't trigger a Pacific-wide alert, despite occurring in the exact same general region that produced a catastrophic ocean-crossing tsunami little more than a year earlier. That distinction isn't a minor technicality buried in a research paper somewhere. It's a live, split-second judgment call made using exactly the kind of depth data at the center of this entire story that determines whether coastal sirens sound from Kamchatka to Hawaii, or whether the event passes as a well-documented but locally contained tremor. So where does that leave the honest, accurate assessment of what happened this week? A magnitude 5.8 earthquake struck a heavily monitored, historically hyperactive stretch of the Kamchatka Peninsula at a depth of 55 kilometers, more than 13 months after the region's catastrophic 8.8 megathrust rupture. It was felt strongly by people near the epicenter. It does not appear to have triggered any tsunami warning, consistent with what would be expected from an event at that depth, whether it ultimately turns out to be classified as an interface aftershock or a distinct intraslab rupture. And it fits within a broader, extensively documented pattern of ongoing seismic activity that scientists explicitly forecast would continue for an extended period following an earthquake of the original main shock's scale, a pattern that has already included multiple magnitude 6 and magnitude 7 aftershocks in the year plus since the initial rupture, and that USGS's own probabilistic modeling flagged within days of the original quake as having better than 99% certainty of producing continued magnitude 5 and larger events well into the future. That last point deserves real emphasis, because it's easy to look at a headline about a fresh magnitude 5.8 earthquake striking more than a year after a historic megaquake and assume something alarming or unusual is happening. The genuinely well-supported scientific reality is closer to the opposite. This level of continued activity is exactly what seismologists expect and explicitly forecast following an earthquake of magnitude 8.8 or larger. Aftershock sequences for earthquakes at this scale don't wrap up in weeks or even months. They can continue producing meaningful, feelable earthquakes for years, sometimes even for decades, gradually decreasing in frequency over time according to well-established statistical patterns that seismologists have documented across dozens of major earthquake sequences worldwide. The 2011 Tohoku earthquake in Japan, one of the most thoroughly studied megaquakes in modern scientific history, continued producing significant aftershocks for well over a decade after the original rupture. Judged against that kind of historical baseline, a magnitude 5.8 event occurring 13 months after Kamchatka's 8.8 isn't an anomaly demanding alarm. It's a data point entirely consistent with how these sequences are known to behave. There's a well-established mathematical pattern underlying all of this, too, one seismologists have relied on for well over a century to make sense of exactly this kind of long-tail activity. It's known as Omori's law, first described by the Japanese seismologist Fusakichi Omori back in 1894, and it describes how the frequency of aftershocks following a major earthquake decreases over time in a remarkably consistent, predictable way, roughly proportional to the inverse of the time elapsed since the main shock. In practice, that means aftershocks are most frequent and often most intense in the hours and days immediately following a major rupture, then gradually, steadily taper off over the following weeks, months, and years, without ever fully stopping in any sharply defined way. That's precisely the shape of what's been observed following the 2025 Kamchatka main shock, an extraordinarily active first few weeks, punctuated by multiple magnitude 7 aftershocks, followed by a gradually thinning, but still very much ongoing sequence of magnitude 5 and 6 events well over a year later. Applied here, Omori's law is exactly why seismologists aren't remotely surprised to see a magnitude 5.8 earthquake occurring in this region 13 months on. It's not an exception to the expected pattern. It's the pattern doing precisely what more than a century of observed earthquake sequences worldwide has shown it reliably does. What genuinely does deserve ongoing scientific attention, not alarm, but attention, is precisely the depth question this event raises. If seismologists studying this earthquake and others like it in the coming months find a consistent pattern of aftershock activity migrating to greater depths, shifting away from the original plate interface and into intraslab territory within the subducting Pacific plate itself, that's a genuinely meaningful piece of the puzzle for understanding how this particular section of the Kuril-Kamchatka subduction zone is processing the aftermath of the largest rupture it's experienced in over 70 years. Since the region's last comparably massive earthquake, the magnitude 9.0 event of November 1952, which itself triggered a devastating trans-Pacific tsunami and remains, to this day, the fifth largest earthquake ever instrumentally recorded anywhere on Earth. Understanding whether the current sequence is settling primarily along the original rupture plane, or increasingly involving distinct fracturing within the plate itself, genuinely does inform how researchers model the region's ongoing hazard, even if it doesn't translate into any specific, actionable warning for people living there right now. It's worth being equally clear about what this earthquake was not, because getting that part right matters just as much as explaining what makes it interesting. This was not a new, independent megaquake threatening the region. It was not associated with any tsunami warning, watch, or advisory. Preliminary damage and casualty assessments for events of this magnitude and depth in this specific region have consistently pointed toward minimal expected impact. The population here largely lives in structures built to withstand frequent seismic activity, a direct consequence of inhabiting one of the most consistently active earthquake zones on the entire planet, where earthquake-resistant construction isn't a specialized upgrade but a basic, long-standing necessity. There's no credible indication that this event signals an imminent, larger earthquake on the horizon. Aftershock sequences, even unusually long and geographically complex ones like this one, don't reliably predict bigger earthquakes to come. They primarily represent the surrounding crust continuing to adjust to stress changes introduced by an event that already happened. What this earthquake does offer, though, is a genuinely useful, real-time window into how modern seismology actually works, not as a field obsessed with predicting the next big one, which remains scientifically impossible with any real precision, but as a discipline built on carefully reading the specific fingerprints each individual earthquake leaves behind. Its magnitude, yes, but just as importantly its depth, its precise location relative to the plate boundary, and how it fits into the broader pattern of everything that's happened in that same stretch of crust before it. A magnitude 5.8 earthquake striking overnight in a remote corner of the Russian Far East might not sound, on the surface, like it deserves much attention beyond a passing headline. But sitting inside the context of one of the largest earthquakes recorded in the past 70 years, occurring at a depth that sits right at the boundary between two fundamentally different kinds of subduction zone earthquakes, it becomes something more genuinely interesting than a routine tremor. A small, specific data point in an ongoing real-world case study of exactly how a section of the Earth's crust behaves in the extended aftermath of one of the most powerful ruptures it has ever produced. That's ultimately the honest, most accurate way to understand a story like this one. Not as a fresh disaster unfolding, and not as evidence of hidden, unexplained danger lurking beneath the surface, but as a genuinely fascinating, ongoing scientific process still actively playing out more than a year after the event that started it, in a place where the ground has been moving, adjusting, and settling. Ever since a fault line 35 kilometers beneath the Pacific Ocean slipped 30 feet in the space of 3.5 minutes. The depth of this latest earthquake doesn't prove anything dramatic on its own. What it does is add one more carefully measured data point to a puzzle scientists have been actively assembling for more than a year, in one of the most closely watched, most seismically significant regions left on the planet. A reminder that even in the long, quiet aftermath of a historic earthquake, the ground itself is still telling a story for anyone paying close enough attention to actually read it.